So our next talk is by Garrett Schieber on the experimental evaluation of heat transfer and mass transfer for the development of lunar thermal H2O mining.
All right. Sound check, can you hear me?
Yes.
Okay. Great. Give me 1 second. All right. So hi again, my name is Garrett Schieber. I'm a PhD candidate at Georgia Tech, and I'm a student on Reveals, and today I'll be presenting part of my PhD work. The focus of my talk is on ice mining, but before we talk about mining the ice, we have to understand the sources of ice on the moon. The earlier talks gave an excellent introduction to how we can characterize and really get the ground truth for this ice. But to give you a quick overview, L-Cross indicated the presence of ice in permanently shadowed regions. And recently, a very good paper came out of class, which indicated, tried to go over a couple key questions. And so we have to know the concentration, we have to know the distribution, and then finally the physical state or the morphology of the ice is needed to be known. And so that recent modeling out of class helped answer a couple questions in terms of concentration and distribution within the regolith. And so their conclusions were just regolith in permanently shadowed regions may contain more than 5% of water ice, and its maximum will be at or below about 50 centimeters of depth. And that also impact gardening may lead to homogeneity. However, ultimately ground truth is needed because we still don't know the exact morphology of the ice within the regolith. Is it particles? Is it a coating on the regolith particles? Is it a sheet? And there's many other possibilities. However, and I don't think this is mentioned a lot, the ice will fill a significant volume, especially if it is at 5 weight percent. And so I prepared a quick demonstration to the right with the average surface porosity of about 0.5. If that regolith is filled with 5 weight percent of ice, the porosity goes down 10% as that ice fills a further 10% of that void space. And that has implications for the design of thermal mining. Now, in terms of mining technologies, when one hears the word mining, they think excavation. And however, I think that excavation will require extensive infrastructure. And to picture that, I see the Lunabotics mining competition. And so if you can see my mouse, here's a promotional image for the Lunabotics mining competition. And you can see that their concept even has an astronaut supporting this lunar mining outpost. And so I believe that for kind of the first generation mining outpost, it's going to be helpful to propose an alternative technology that does not require excavation. And that alternative is thermal mining. And so thermal mining, again, does not require excavation and is fairly simple as essentially regolith and ice are heated. In this case, I'm showing concentrated irradiation as the heat source, and that would be reflected into these permanently shadowed regions. And that heating causes ice to sublimate. Sublimation is, of course, the phase transition from solid to vapor. And that vapor then sublimates out of the regolith and then is funneled to a cold capture tank shown here on the right. And the funneling occurs as there is a semi-transparent capture tent that doesn't allow volatiles to escape into space, but also allows that concentrated irradiation to strike the surface of the cold icy regolith. And so even though it's a fairly simple design, there are still engineering challenges associated with design of thermal mining systems. And so the important physics in play here are heat and mass transfer. And so accurate models are needed to assess both heat and mass transfer to assess the feasibility and optimize the design of thermal mining systems. And so porous media, and this is complicated by the fact that porous media are inherently random and difficult to model. And so experimental study is needed. I should provide an image of JSC1A just so we can show how inherently random porous media are. And so now the first aspect of the physics I would like to talk about is the mass transfer, and the mass transfer specifically of the volatiles within the pore structure of the regolith. And so mass transfer within a porous media can be modeled with the advection diffusion model shown here, where the first term is the advection term and the second term is the diffusion term, where at low pressure, diffusion is dominant. However, because we want to be sublimating this stuff, higher pressures may be more relevant. And in that, advection can significantly enhance transport. And furthermore, the tight pore space can lead to moderate high pressures, at least locally. And so both, in addition, both of these advection and diffusion rely on experimentally determined coefficients. And so in a previous work, I've determined experimental coefficients used in transport. And just to give a quick overview, I'd like to draw your attention to the plot on the right. On the y-axis, we can think of this as the transport coefficient, where a higher transport coefficient corresponds to less resistance to flow, and a lower transport coefficient corresponds to less resistance to flow. And so the Knudsen number, or more resistance flow, excuse me. And then on the x-axis, we have the Knudsen number, where the Knudsen number is a ratio of the mean free path to the wall diameter. And another way we can think about this is essentially the ratio of the distance between molecules to the distance between particles within your porous media. And so at very low pressures, the distance between molecules is very large. And so a high Knudsen number corresponds to very low pressures. And so what we see is that at the highest Knudsen numbers, we have very limited transport. And as we move to higher and higher pressures, the advection kicks on and enhances our transport. And so these results are shown for nitrogen. And nitrogen was the first step towards moving towards the more complex H2O, because both nitrogen and H2O will both have advection and diffusion. In addition, terms such as permeability are gas independent. And so H2O experiments are currently in progress to measure the gas dependent slip and additional H2O specific phenomena. Unfortunately, this aspect of the project was delayed due to COVID. So moving on to heat transfer. Heat transfer in thermal mining can occur in the following pathways: a conduction between regolith particles, radiative heat transfer within the packed bed, heat transfer through any gases in the interstitial pores, and then finally conduction through the ice itself within this icy regolith. And so all of these mechanisms for heat transfer have different orders of magnitude in terms of how much they contribute to the overall effective conductivity, heat conductivity of this packed bed of icy regolith. And the first one and the lowest one is the pure conduction through the regolith particles themselves is fairly limited, on the order of 10 to the minus 3. And then the radiative exchange, when normalized to the temperature gradient, we call this the effective radiative conductivity, can enhance this conductivity all the way up to about 10 to the minus 2. And then depending on the pressure of the gas within the pores, conductivity can be enhanced all the way up to 10 to the minus 1. However, for the majority of the cases, it's on the order, it's much, much lower, as with no gas, you can't have conduction through that gas. And then finally, the most interesting mechanism, I believe, is the conduction through the ice. And that's because ice has conductivity on the order of 1. And in fact, ice may form bridges between particles, enhancing heat transfer into the regolith, and essentially providing a pathway for that heat. And so to kind of measure this, direct temperature measurements coupled to a solar simulator to kind of demonstrate this thermal mining are envisioned. I was hoping to get this done within the scope of my PhD, but I think due to COVID, I will have to nix this aspect, but hopefully another student can come along and continue this project. However, the work situation has led me to develop a model for thermal mining. And so to give a quick overview of this model, we have regolith, packed bed of regolith, where I'm modeling right now, or just providing a snapshot up to 75 centimeters, where at around 50 centimeters and beyond is where we're really going to start seeing high concentrations of water ice. And I provide a solar heat input of 10,000 watts per meter squared, and a time from start in this transient model of 6 hours. And the results of this model are shown here, where on the top x-axis, we have the temperature. And so at the surface, we get a temperature of 550 Kelvin. And then we have a significant temperature drop all the way down to about 225 Kelvin, in which the temperature levels off. And then on the bottom x-axis is the density of ice in each cell, or the concentration of ice in kilograms per meter cubed. And so we see that we've completely desiccated the top six centimeters of regolith, but then we see a small spike in ice concentration, and then it levels off to the value in which I initialized it at. And so basically what's happening here is, as we desiccate this edge layer of regolith, we remove the heat pathway as in the ice. And so then we rely solely on the radiative conductivity and maybe any conductivity contributions of the gas, which is fairly limited. And this leads to a significant thermal resistance, essentially meaning our heat cannot penetrate very effectively to the maximum. Now, I wish I could get into this more. However, this model details and engineering solutions to try to enhance this heat transfer and hopefully get around to this 50 centimeters depth are discussed in upcoming work that I'm developing. So in conclusion, ground truth and prospecting are needed to determine the ice content, the distribution of the ice, and the morphology. Further experimental study is necessary to refine both the models I presented for heat and mass transfer. And thermal mining is a promising option. However, like I showed in the last slide, engineering solutions need to be developed to enhance the heat transfer into regolith. Right? And that's all. Thank you.
Thank you, Garrett. So we have 2 questions in the chat, and I think we have time probably for one of them, and the other can wait till the discussion section. So Caitlin Arndt says, for your H2 experiments, at what temperatures are you working under?
For, I'm working at, okay, so we're talking over here. Those experiments, I'm working at a higher temperature because the thermal mining process is proposed to take place at higher temperature. And another reason too is a practicality reason. As I try to measure this gas, I don't want condensation or deposition in my vacuum chamber. And so I'm right now measuring at about 100 degrees Celsius or 373 Kelvin. So.
All right, thank you, Garrett. So we will move on to our next talk. And if you have more questions for Garrett, you can bring them up in the discussion section.